not gonna speak. Okay. Muna. Sige na.
Wala mo nakatap. Kanina. Yung ano, may kanina tayo.
Dito sa gitna.
Nasaan na yung luggage? Nasaan na yung luggage? Yun yung issue na.
Kaya na gawin yung ano.
Ang ina.
Pusla ka, habot mo yan. Main box.
Two.
Come on.
Attention. Attention to all delegates. This room is belonging to the science behind climate change. Please make sure that you have already registered. If you are on the global coal outlook, then please go to the Maui. And if you are on the energy storage, then please go to Tanjung Benoa. The session will be start 2 minutes. Attention, attention to all delegates. Please have a seat because the session will be start soon. Thank you. Attention, attention to all delegates. Please have a seat because the session will start soon. Thank you. Good afternoon, ladies and gentlemen. Welcome to the session, and the title of the session is "The Science of Behind Climate Change." And I'm glad to be your host of this session. Nowadays, the climate change is hunting us. Climate change is happening, and the important thing is people has a significant role on creating it. The science has been proved that all of this impact is real. This session will provide us the scientific understanding of climate change, the natural system, the cause, the outcomes, and how we can tackle it. Please welcome them onto stage. The first one is Mr. Koh Tae-hyung as Associate Professor from NTU. And the second speaker is Ms. Jian Palutikov as a Director of the National Climate Change at Griffith University. And the third is Mr. Nikhil Advani as a Senior Program at World Wide Fund. And fourth is Mr. Hari Susanto as a representative of Perwaku. Our first speaker is Mr. Koh Tae-hyung. The floor is yours. Please give applause.
Okay. Thank you very much for coming for this session after lunch. I hope you will not fall asleep. I'll try to keep you awake. Well, I'm trying to move it to the first slide. But in the meantime, I'm from Singapore. I'm from Nanyang Technological University. I have a course on climate change and climate science where I teach. So some of this material is taken from that course. So this is the topic, basic science of global warming. It's not advancing. Okay, so the remote doesn't work, so I'll just use a verbal cue. I'll say next, then you advance the slide. So next, please. Yes, so we'll start off with a very basic understanding. We have basically radiative balance between the incoming radiation and outgoing radiation for the atmosphere and the planet Earth. And so the amount emitted must equal the amount that's absorbed. But we must bear in mind the amount that is absorbed is the net of what we receive and what we reflect away, because we don't absorb everything. We reflect about 30% of the radiation back to space. Next. So when we talk about reflection, this is the factor known as albedo. It is the fraction of the light that's incident that's being reflected. So the albedo comes from the surface of the Earth itself. Next. Next, please. Yes. So you have, can you go back? Yeah. So the surface itself. Yeah, okay. So the surface itself, the bright surfaces like deserts, like ice-covered land, they reflect a lot of radiation back into space. But the dark surfaces, like the surface of the sea or forests, they are quite dark and they absorb most of the light. So you know that for changing land use pattern, changing land cover by vegetation, if you deforest, that would remove the dark surfaces, replace it by bright surfaces. So that would change the balance of radiation in the atmosphere and on the Earth. But besides what's happened on land, there's also the clouds. Clouds reflect a lot of light back into space as well. So this is the cloud albedo. And the higher the cloud is, there are two kinds of clouds. There are high clouds and then there are low clouds. And they have different effects. Because clouds are complicated things where they also absorb radiation from the Earth itself. So when clouds absorb radiation, they re-radiate the infrared radiation back to the Earth. That tends to keep the Earth warm. So on one hand, clouds reflect solar radiation back into space. That makes the Earth a bit cooler. But on the other hand, it also absorbs radiation from the Earth. That keeps the Earth warmer. So clouds has two competing effects. And the two types of cloud have two different net effects. The higher clouds tend to keep the Earth warm, whereas the lower clouds tend to cool the Earth. All right? So that's the basic understanding. So when we disturb the climate pattern, we disturb the cloud distribution and the cloud heights, we also change the way radiation interacts with the atmosphere, and hence lead to climate change. So the higher clouds are the wispy cirrus clouds that you see in the upper diagram, and the fluffy cumulus clouds are low clouds. Now, so when you look at radiation, you will see this picture very often, where it basically shows when you have the amount of radiation coming in, something that averages to about 340 watts per meter square over the whole surface of the Earth. There's a fraction, the 30%, that is reflected, and I've said that if you change the surface conditions, you would change the amount reflected. But very importantly, there is a lot of radiation that is emitted from the surface of the Earth, that's absorbed by the atmosphere and re-radiated back to the Earth. Now, this is one that is causing the warming. When you increase carbon dioxide, what it does is that it absorbs this infrared radiation from the surface of the Earth and then re-radiates it back to the Earth. It's just like you standing in front. If you have a furnace and then you put a reflector around the furnace, it would reflect the heat back towards you. So it's the same effect. That's why the Earth's surface gets warmer when you increase the carbon dioxide. It's because of this effect of absorption and re-emission backwards to the Earth. But if you look at the atmospheric component carefully, you look at the numbers there, the component that actually warms the atmosphere itself, so we are not talking about the surface now, it's the atmosphere above. The component that warms it comes mainly from condensation of water. When you form rain or when you form snow, water vapor changes back to the liquid or solid state, and it releases heat. That warms the atmosphere. So therefore, in your mind, you must distinguish between warming of the surface and warming of the atmosphere. Warming of the surface is by this radiation that's absorbed and re-emitted backwards to the Earth. Warming of the atmosphere itself is mainly by the release of latent heat when water vapor converts back to solid or liquid. And right now there's a small imbalance, that's why we have warming effect. In terms of what gases are responsible for the radiative effects, water vapor is the most important player. It's about 1 to 4% of the atmosphere by volume. And in this water vapor is actually responsible for keeping the Earth warm. If not for water vapor, the Earth's surface would be 35 degrees Celsius cooler. So this is very important. For life to exist on Earth, you need water vapor to keep the Earth warm by absorbing and re-emitting the infrared back towards the Earth's surface. But carbon dioxide is much in the media. It is also a greenhouse gas. It's about 100 times less abundant, about 0.04% by volume. Now, it is important because, you see, water vapor is around all the time, and this water vapor basically blocks the escape of infrared radiation pretty much throughout the whole spectrum, apart from a small window around 8 to 14 micrometers. Now, in this small spectral window, where the infrared light escapes to space, carbon dioxide absorbs. So when you change the carbon dioxide content, what you find is that it's like this small door by which radiation escapes. You control the opening of the door. So you control to a final degree, a few degrees Celsius of change. And that is enough to bring out your ice ages in the geologic past. Just by varying carbon dioxide, you have a few more degrees Celsius change, and you have all your ice ages. So carbon dioxide plays this vital role, controlling the opening of this window of escape for infrared radiation. And we have to mention ozone as well, which is very abundant in the next layer of the atmosphere. We call that the stratosphere. So the stratosphere is the layer of atmosphere above where we have our normal weather, which is called troposphere. So above the troposphere, you have the stratosphere, and that's where ozone is. And ozone is responsible for absorbing the solar radiation and making it warm up there. Okay, temperature actually increases with height in the stratosphere. So just now I mentioned about how the Earth's surface was kept warm by water vapor, first of all, and then to a final degree by carbon dioxide. But how about the atmosphere itself? So as I said earlier, the atmosphere itself, radiatively, water vapor is very important, and the net effect of water vapor is that it cools the atmosphere. It emits infrared radiation back into space. Okay? Carbon dioxide is not so important for the atmosphere itself. Water vapor is. But the net effect of water vapor is to cool the atmosphere by emitting radiation into space. So what warms the atmosphere is really the formation of ice and snow. When your change of phase of water occurs, it warms the atmosphere. And this component is one that is causing the troposphere, the lowest layer of the atmosphere, to warm up. Okay? And how about in the stratosphere, the next layer? Well, here, ozone absorbs the solar radiation, and carbon dioxide mainly emits infrared radiation into space. So between the absorption by ozone and the emissions by carbon dioxide, we have a balance in the heat in the stratosphere. But because when we increase the carbon dioxide in the atmosphere, we increase the component that's meant to cool the stratosphere. So what you see is that in the stratosphere, you have cooling. So the changes in atmospheric composition, we have seen a rising trend in carbon dioxide. I think everyone knows this. This graph is updated between 2013 and 2014. And later, Jim will show you even a latest graph where after the winter season, you have even more carbon dioxide because the leaves and the vegetation decays and release carbon dioxide after winter in the northern hemisphere. So the other thing that is less in the media is that in the stratosphere, water vapor is increasing. And you see, the stratosphere normally, where does water vapor come from? It comes from the oxidation of methane. When methane oxidizes in the stratosphere, it forms water vapor. So the rising water vapor in the stratosphere is an indication of increasing methane, basically. So we have carbon dioxide increasing and methane increasing. These are greenhouse gases. They cause the surface warming, which you see in this picture, which I think Jean will show again. These are observations of the surface temperature trends covering ocean as well as land. And you see that almost everywhere there has been an increase in temperature over the last 100 years or more. What really tells us that CO2 and greenhouse gases are responsible for this climate change is this graph, this set of graphs, where in the upper graph, you see the stratospheric temperature decreasing. These are measurements from satellites as well as from balloons, weather balloons. So it has been decreasing, whereas in the lower graph, you see the temperature kind of increasing in the troposphere. And according to our explanation just now, if you look at the atmosphere itself, the stratosphere has more carbon dioxide. Carbon dioxide emits infrared radiation to space, When you increase carbon dioxide, you increase the cooling in the stratosphere. At the same time, when you increase carbon dioxide in the troposphere, they warm the surface. When the surface warms, more evaporation happens. More water vapor goes into the atmosphere and ultimately condenses, warming up the troposphere. So the troposphere will get warmer. So the same key factor, CO2, is responsible for both for the cooling in the stratosphere, the warming of the surface, and the warming of the troposphere. So this single explanation that explains three trends, one in the stratosphere, one in the troposphere, one on the surface. And these trends increasing and decreasing, this forms a very good explanation for what we observe. There are very few, in fact, there are no other explanation that can explain so simply this set of observations. So some people might want to think about, oh, maybe the sun is getting stronger, there's more radiation from the sun, but that wouldn't explain cooling in the stratosphere, for example. So by now, this is like fingerprints of the carbon dioxide as the so-called culprit responsible for all these climate change that we see. And going forward in time, if you look at the projections, the temperature increase for now will be kind of increasing linearly with the total carbon dioxide that we have accumulated in the atmosphere. So if you emit more and accumulate more, you would have higher temperature rise. And various projection scenarios have been put forth. The black line is the observation. The light blue, the dark blue, the red, they are projections. And the one that I think is more likely is actually not the most optimistic projections. So if you can see the numbers, it looks like it's slightly above 0.5 degrees Celsius when measured against 1861 kind of baseline, pre-industrial baseline, okay? And finally, how important is this rise in temperature? We just have to look at what happens for thousands of years before. The blue line is actually a model that has assimilated data for the past 10,000 years. And you can see that the end of Ice Age happened around 8,000 years ago. That's where the green vertical line is. And since then, the Earth has been cooling slightly, moving towards the next Ice Age. But in the last 2 centuries, essentially, we have undone all the cooling. That's the red line from instrumental records. We are back to where we started when the Ice Age ended. So that is quite important. So with that, I thank you for your attention, and later I look forward to your questions. Thank you.
Okay, I will remind you, there are 2 ways to ask the question for the speaker. You can use Twitter by mentioning us at ISES with the hashtag ISES and hashtag science. Or you can ask directly to the speaker after all of the speakers presenting their presentation. So let's move to second speaker. The second speaker is Ms. John Pautikov. Please welcome. Give applause.
So thank you very much, Mr. Chair. I'm Jean Palutkov, and I come from Australia. And I'm just going to talk a little bit about the same sort of things that the previous speaker addressed, but I'm just going to take a slightly different take on it. So if I can get my presentation up, we can go. Thank you. So here we are to talk about the science of climate change, and I'm just going to talk a little bit about what is the problem and where are we headed. And just thinking a little bit about climate change, so the previous speaker spoke almost entirely about the greenhouse effect. Of course, there are many causes of climate change which are natural, which are not caused by human beings. And I think since we're here in Bali, we have to mention Mount Tambora. So it's the largest, most powerful volcanic eruption in recorded history. Took place in 1815, so we're actually here in Bali, just 300 kilometers away, for the 200th anniversary of that explosion. And it is widely considered that it caused a reduction in temperatures of around half a degree in the following couple of years, led to widespread harvest failure, and many people died directly on the islands of Indonesia, and many more died because of famine. So there are natural causes of climate change, and that one was worth a mention, but here we're going to talk more about the greenhouse effect. So we have already heard what is the greenhouse effect, so I'm not going to bother with this slide. I'm just going to carry on. You've seen that. And you've seen that. So you understand now, I'm sure, that we have shortwave radiation from the sun, and greenhouse gases are transparent to that shortwave radiation, but they're not to the long-wave radiation that goes out from the Earth. They absorb it and reflect it back, and therefore, if you keep adding greenhouse gases to the atmosphere, it keeps getting warmer. And this just shows you, it's taken from the Intergovernmental Panel on Climate Change, their third assessment their fifth assessment, Working Group 3. This shows you just some of the sources of greenhouse gases, and you can see, if you can read a text, that the primary sources of greenhouse gases are industry, especially electricity generation, transport, and agriculture, forestry, and land use. What effects has it had? Well, if we just look at the observed record, it shows you this is global land and sea surface temperature record. It's collated from many observational records, goes back to around about 1850, and shows you that over the period of record there has been a warming of about about 0.7 degree Celsius. And you've already seen these spatial patterns with the warming concentrated at, so this is the observed record again, concentrated at high latitudes and over continental regions. And the only area where cooling has been observed is in the high North Atlantic. We do hear a little bit about this hiatus that's taken place in the warming record since about 1998. In fact, just last week in Science, a paper appeared which reanalyzed all the observed data and showed that perhaps the hiatus is in fact an artifact of the method of collating these records. And I'm sure that many scientists are going back to look at the data again. But the fact remains that you may see, or you may not, depending on whether this paper in Science stands up, pause in the warming in the observed record, but if you go elsewhere in the data, then you will find that the warming has just continued over time. So here you can see the record of ocean heat content in the top left, and in the bottom right you can see the record of Arctic ice extent. And you can see that over time those records are inexorably progressing towards more serious conditions. They show no sign of hiatus. A great deal of work has been done by the Intergovernmental Panel on Climate Change to explore the impacts of climate change, and this just shows you one figure which appeared in Working Group 2, the fifth assessment. That's the Impacts Working Group, and this tries to show you where we have actually observed the impacts of warming, whether over land or sea, or whether sea ice retreat. Nevertheless, you can actually observe changes that are taking place. For example, failures in harvests, changes in terrestrial ecosystems, changes in the distribution and size of fish stocks. And in fact, I did find a presentation, an article in the Jakarta Post that looked at the impacts of climate change as they have affected and will affect Indonesia. So, where are we headed then? Well, in order to understand where we're headed, we have to look at computer-based models of the ocean and the atmosphere. And this just shows you what those three-dimensional models of the Earth and the atmosphere look like. And they actually look through the depth of the atmosphere, and they look right round the globe to model our future climate. But we have to tell those models how we think emissions are going to track out into the future. And these are the latest ideas of how emissions of greenhouse gases are going to track out into the future. And you can see people look across a whole range of possibilities, because it's very hard for us to tell what will happen. And depending on what those possibilities are, that dictates what those models tell us about how temperatures will evolve out into the future. And so you can see that for the very worst, most serious, most high levels of emissions of greenhouse gases, we expect that temperature, if we just keep on the way we're going at the moment, will increase by about 4 degrees Celsius by the end of the century. And if they do that, this gives you some idea of what will happen to our temperatures. So this is for two scenarios. The one where we really try very hard to limit our greenhouse gas emissions, where there's a real shift towards renewable energy and there's a pause in deforestation. Then you can see over on the left-hand side graphs for temperature at the top and for rainfall at the bottom. And on the right-hand side, you can see what will happen if we track along that upper graph that I showed you in the previous slide, and how serious the warming will come to be, and the very strong effects that there will be on rainfall, especially in very high latitudes at the poles, but also around the equatorial Pacific. And there will be quite severe effects on oceans, so sea levels will rise, partly because of thermal expansion and partly because of melting sea ice, land ice, and that will have effects on coastal settlements, flooding. Many people now live in megacities and in very low-lying areas along estuaries. There is acidification of the ocean because the additional CO2 that is released into the atmosphere by our activities is absorbed into the oceans and causes acidification, which has effects on coral reefs, in particular the ability of shell-forming organisms to actually make shells. And we will have warmer ocean waters, which will have effect on fish abundance and on distribution. And this is a picture from the Intergovernmental Panel on Climate Change again, and this is looking at future impact. And you can see that it's telling us that there are strong effects for Asia on the likelihood of flooding, on the risks to infrastructure, and also on our the effects of more severe and more frequent heat waves on human health. So how much warming is too much warming? Well, this is a quote here from the UN Framework Convention on Climate Change, which is the international convention that tries to limit our emissions of greenhouse gases. And there is a session in this conference, I think, on Saturday morning about the Paris meeting that will take place at the end of the year, and that's a meeting of the Framework Convention. And that convention is of the opinion that we should work very hard to avoid dangerous climate change, and it defines dangerous climate change as 2 degrees Celsius above pre-industrial levels. And as I told you, if we keep on tracking the way we're doing, our temperature rise by the end of the century will be 4 degrees. So we're not in a good position with respect to limiting our temperature increases and the other effects that there will be on our climate. So this shows you some possible pathways out into the future that we might track along, and how those, in terms of our emissions, and how those might affect temperature change. And essentially, looking at this graph, we have to track along the yellow shaded area if we're going to have any chance of limiting emission, or we're going to have a good chance of limiting our emissions to 2 degrees. And so here there's some information about how we can do that. Essentially, we have to, if I can just read this, by 2050, globally, we should limit emissions to between 40 and 70% of 2010 levels. And by the end of the century, we should have totally decarbonized our society. That is to say, our emissions should be down to 0. How are we doing? Well, in the graph on the right, you can see that you can see the future scenarios that I have shown you in previous slides. If you look at the black blobs, those show you the observed global temperature changes. And as you can see, we're happily tracking along the upper line that will deliver 4 degrees of warming by the end of the century, whereas we need to get onto the bottom line if we're going to have a good chance of limiting temperature increase to 2 degrees above pre-industrial levels. Okay, so the messages I would like you to take away from this presentation are these. That global climate change is happening, and that we are calling it. We're on track at the moment for 4 degrees of warming by 2100, and to have a good chance of remaining below 2 degrees of warming, that we need to decarbonize our economies by the 2080 to 2100. And at the moment, there is too little action. And just at the bottom there, that shows you the promises that governments have made with respect to limiting their greenhouse gas emissions. And you can see Australia there, which is where I come from, not looking in a very good position, in fact, looking in an absolutely shocking position. And you can see Indonesia there, which has ambitious targets for limiting greenhouse gases, particularly when you consider it's a developing economy. Thank you very much, ladies and gentlemen.
Thank you. That's such a great presentation from Mr. Ko Tae Young and Ms. Gian Paltikov. So, the third speaker is Mr. Nikhil Advani. Time is yours.
Great, thank you. Thank you for inviting me to this conference, and thank you all for attending this session today. I'm a bit unique that I'm a biologist. How many biologists do we have in the room? Oh, cool, 2. How many of you wish you were biologists? Yeah, awesome. Well, let's see, maybe this will change your mind. So I'm with the World Wildlife Fund in the United States. I'm based in Washington, D.C., and I'm a... That's not... Can we go to the beginning of the presentation? That's the end. It's the same slide at the beginning, so. I'll just go through it myself. Okay. Okay, well, in the meantime, so I'm a senior program officer working on climate change adaptation for World Wildlife Fund. I did my PhD in biology, and my PhD was on getting a better mechanistic understanding of how species might respond to climate change. So a lot of the focus of my talk today will be on how climate change is impacting biological systems and how we can help them adapt, and also a bit about their natural capacity to adapt as well. Okay, so just to give you a brief history of global warming, this isn't something that's new. This is something that for over a century, you know, we haven't known that humans are causing it, but there's been all these small steps that have built up our knowledge in it. So as far back as 1824, Joseph Fourier he discovered that the Earth has some sort of a layer that's actually allowing it to be habitable. Otherwise, given its distance from the sun, it would be far too cold to live here. So that's 1824. In 1859, John Tyndall proved that CO2 had an insulating effect, amongst other greenhouse gases like water vapor. So the idea is that, if you have CO2 and then you have a heat source, CO2 can actually help to trap that heat source. Okay, so that was 1859. And then towards the end of the 19th century, 1896, Svante Arrhenius actually suggested that increasing CO2 in the atmosphere is actually causing surface warming on Earth. Okay? So over 100 years ago, we've already known about this phenomenon, and amazingly, today, people still deny it. So you've already seen that figure on the right that shows you the warming that's occurred over the last century, and then on the left shows you the increase that we've had in carbon dioxide emissions. And there's often a misconception that we can actually stop climate change from happening. So that's not true, right? Climate change is something that's already happening. It's something that's going to get a lot worse if we don't do anything about it. And the way I actually work on adaptation. And the way I like to think about it is that climate change is happening, and we have to learn how to deal with it. And if we don't mitigate, then that red line that you see up there, that's what we're going to be dealing with, and it's going to be a lot worse. If we do actually mitigate our greenhouse gas emissions, then we might actually get to somewhere around that blue, not, okay, it's a bit tricky there. But if we shoot for 2 degrees of warming, that is, that's sort of the target that we're aiming for at the moment. So the difference between that and, whatever the 6 degrees of warming that we might see, that's what mitigation is going to help us with. But the 2 degrees that we're already going to experience in all likelihood, that's what adaptation is going to help us deal with. Okay? Okay, so just to highlight the problem, again, when people talk about climate change, they often talk about it and suggest that we can actually stop climate change from happening. This is what we call the greenhouse gas warming potential of different greenhouse gases. You have the warming potential over 100 years, which factors in the life of the greenhouse gas itself and also the actual warming effect of that molecule. So they use CO2 as a baseline of 1, and then you see that methane, water vapor, and finally CFCs have a much higher warming potential. And in many cases, it's because they just last for so long, right, in the atmosphere. So it's going to take a long, long time for them to break them down. So even if we stopped our warming, our emissions entirely today, we will still see warming for decades or centuries to come. And that's what climate change adaptation is learning how to deal with all of that. The other thing is, we often talk about warming in 2050 or 2080, and I work in conservation, and when I'm out in the field and I go up to our field staff, if you show them a map of a species and say, okay, this species is going to be here in 2080, well, what are they supposed to do about it, right? They're dealing with far more urgent threats like poaching, habitat destruction. So what we at World Wildlife Fund and a lot of agencies like NOAA are increasingly starting to do is to communicate climate change through extreme weather events to highlight that it's already happening. So this is just from April. It shows you some major climate anomalies from around the world. Since then, there's been, so if you look at the United States over there, it shows you drought. In Texas, we've had massive flooding. They had enough rain in May to cover the entire state of Texas with 8 inches of water. And prior to that, Texas was in the midst of 7-year drought. Okay, this is extreme weather. This is climate change. And in other parts of the world, we see massive droughts, right? We're now entering an El Nino phase. That's also going to cause a whole lot of disruption. So I think this is a nicer way to communicate, not nicer, but it's a more effective way to communicate what we're actually dealing with. You've already seen this slide. It just highlights the impacts on biological, physical, and human systems that we've already observed. And like I said, I work on in biology, and I'm more interested in the impact of climate change on biological systems. So we are seeing a lot of things happening. We're seeing species shifting their ranges. They're shifting towards the poles and shifting to higher altitudes to maintain climatic zones that they're more accustomed to. We're seeing coral bleaching. I was just diving up in Koh Samui 2 days ago, and you see a lot of coral bleaching, and the water was extremely warm. We're seeing species extinctions that are partly attributed to climate change. Golden toad went extinct And it's thought that part of what contributed to that was this fungus which colonized its habitat, and it never used to be there previously. And then you're also seeing changes in phenology or changes in timing of events. And you can't quite see that graph at the bottom very well, but what's showing is different groups of organisms, like plants and amphibians, and showing how they're advancing their annual life cycles. So for example, birds are laying eggs earlier in the year than they used to. Plants are flowering earlier than they used to. And this is what we call change in phenology. Okay, and human systems. So I am increasingly becoming focused on water. And just because we're doing a lot of work in Africa, and in terms of temperature, we are seeing changes. We're actually interviewing communities to see the kinds of changes they're experiencing. But the ones that really seem to be affecting them the most tend to be changes in rainfall. So just to give you a quick snapshot, in Kenya, parts of the country are in the midst of a huge drought. And then in neighboring Uganda to the west of the country, that picture that you see on the right over there, they have massive flooding. That's at the foothill of the Rwenzori. I was there last year, and that bridge that you see in the foreground was one that was constructed because the previous one got washed away. So they had one single stream from the mountains that, over the course of that single flood event, turned into 4 different streams. Okay, so climate adaptation. There's many definitions out there. It's essentially actions to reduce vulnerability to actual and expected changes in climate. So I talked briefly about some of the impact that we're already seeing on biological systems and human systems. And I'll quickly talk about what we can actually do about it. So from a species perspective, animals and plants have the capacity to adapt. We have to sort of help facilitate that. So in many cases, there might be particular genotypes. Let's say in coral, we're now finding that certain coral genotypes are actually quite tolerant of heat. And over time, those might become more and more frequent, right? More common in the population. But we have to allow that to happen. So we have to mitigate other threats like destruction of coral reefs, such that we can actually maintain that genetic diversity. So the species have natural capacity to adapt, but just because humans are interfering so much with ecosystems today, we actually have to do a lot of interventions on our own. So this is a nice example. I was just in Thailand this week, and in Khoi Buri National Park, we're building what we call check dams. And to the left of your screen, that's an example of a check dam. So these are seasonal streams. They're not year-round. And what they're doing is they're building these concrete barriers, and then they dig in a bit before that, so that when it rains, water accumulates in the stream. What it also does is it keeps elephants in that side of the park. So that elephant actually was probably about 500 meters away from that. Unfortunately, I didn't get a picture of the elephant drinking. That would have been perfect. But it keeps elephants in that part of the park, and it also helps to keep them away from the more permanent water source, which is in the northwestern part of the park, and that's actually where human communities live as well. So it helps to mitigate human-wildlife conflict. And I deal with a lot of cranky old conservation biologists, which is why I love it when I come and speak to young, energetic students like yourselves. And when you deal with these people, they're so stuck in their traditional ways of doing conservation that a lot of them, when I've presented this example of work that they're doing, they say that, elephants are fine. They've dealt with drought for eons, and they'll be fine in the future. And it's true, elephants have an amazing capacity to find water, but we are altering their landscape so much, and we're now seeing droughts on such an unprecedented level that these are things that we've never seen before, and we really need to learn how to deal with it. And then lastly, so that's biological systems. Lastly, looking at human systems. So again, what you see on the left there is in Thailand. I was just there. And this lady told me that it's become too hot for her to farm during the day. So whereas she used to take a break from like 12 to 2 or something, she now has to take a break from about 12 to 4 because it's just too hot to farm. In Kenya, there's a village that's adopted a nocturnal lifestyle. Kids go to school at 6 in the morning and are done by noon. And then they go back to school at 6 p.m. because it's just too hot during the day. So there's many things that we can do. On the right, I gave you that example of flooding in Uganda. Over there, they're moving further away from the stream. So they've been told to move the settlements a certain distance away from the stream. And they're also planting trees as a barrier between themselves and the stream. So there are things we need to do, and in adaptation, we're doing very little. There's a lot of talk. There's plenty of publications. There's lots of conferences where we get together and talk about it, and very little is being done. So it's something that really needs to change, and hopefully things are changing. And that is it. Thanks.
Thank you for Mr. Nikhil Advani. And the last speaker is Mr. Haris. And please welcome.
First, thank you for attending this presentation. Actually, the three guys talking about the problem. What is the problem? CO2, carbon dioxide. My presentation is going to discuss is about how to solve the problem. This is part of it. First, I would like to introduce myself. My name is Haris. I work for the Perwaku. Perwaku is Indonesian Environmental Intellectual Association. So this organization is run by Pak Doni Yuskiantoro, and I'm the treasury on that. But part of this environmental activist, I run my own business. That is the research is funded by our own company. I just want to talk a little bit about the vision mission as Perwaku. It's realization of civilization that purify the environment for the sustainable life. This is the vision of my organization. But if you would like to know more about Perwaku, you can please see our web. What we'll discuss, I would like to present, we call it electron injection technology for CO2 converter. So this is 7 or 8 year research, and a lot of effort, a lot of money we put on it. But because I'm the practical researcher, I would like to do the research that I should able to be sell to finance my research, and back to the research. This electron injection, because if we could able to inject the electron to the carbon dioxide, it's going to be changed even to go to the syngas or methanol or methane that we are able to use as the energy. This is the idea. Inject the energy and come back to the energy. This is like photosynthesis. In the photosynthesis, you produce the hydrocarbon, carbohydrate, but then here we call it electrosynthesis. We produce the CH4 or methanol. But in our research, we try to produce the methane. Even though that methane also part of the global warming of component. But this is the easiest ways based on our research. I think everybody know about this carbon cycle. I don't want to talk more about that because this is you can find everywhere the information. Why CO2 technology? As I said that my research should be a customer focused. Then customer asked me to do the research, and I do that. Because some reservoir in Indonesia and Malaysia have CO2 gas various presented in crude and gas analysis. For example, North Sumatra Block A has about 15 TCF reserve, that is used reserve gas, with minimum 65% of CO2. And if student from Malaysia, the student from Malaysia, raise your hand. Oh, okay, unfortunately no. This Petronas Kifeh project in Malaysia. The Petronas already allocating $1 billion to export and exploit 200 MSCF a day gas, but 70% of it CO2. And then this is for the current in Pertamina. They produce 70 to 80% gas, but 20 to 30% CO2 on that. This is very, very huge CO2. So, what are we doing? Our research team has working to develop a technology called electron injection technology. The objective to recycle the CO2 and to produce the alternative commercial gas. This is done about 7 to 8 years ago. The result of the research demonstrates the good result to aim to construct the pilot unit. We aim to construct the pilot unit 5 MSCF CO2 gas rate and become the first developer technology and gas industry. So actually we have already have the mini unit. So we are now to do the designing for the MSCF. This is about 1 to 40, but this is enough to represent the real case on the operation of the unit. What are the KPI for the commercialization? We call it, we are going to run this one. What is KPI? Then the unit is able to solve the customer. This energy consumption, first is energy consumption. This we aim to get at least maximum 1.6 gigawatt per million ton of CO2. So we already track the rate from this rate. That's actually we are able to solve this energy consumption. The second is the footprint. So footprint is very important. Then we now still designing how to make it as small as possible. So it's able to be located at the offshore operation. And then the third is reliability. At least 2 years without any problem, without changing we call it the catalyst or solution or producing a lot of waste, something like that. So all this parameter we have done it. So for the small unit, we are now designing for the 5 MSCF unit. That some going to be happen very, very, very soon. Thank you very much.
Okay, that's a great presentation for all speakers. Okay, this is a follow-up question from me to all of the speakers. Is it possible to fix climate change? Is it possible? How we can make the environment back to normal? Okay, that's a follow-up question.
Wait, your question is, can we make the environment better? Make normal again? Normal as in defined as in pre-industrial, or how normal is normal? Yeah, so you see, that's a very kind of good question to ask. And then it makes us think, what's normal, right? I showed the last slide, the world is, I think, was supposed to get cooler after the end of the ice age, right? It's supposed to get cooler slowly. So the question is, can we return to that cooling trend? It will be probably not in 1,000 years, okay? Because the CO2 is there for a few hundred years, and then whatever heating that has gone on that is absorbed by ocean and brought down to the deep ocean, it takes about 1,000 years for the circulation in the deep ocean to go one round. So for the whole system to re-equilibrate and go back to normal, it will be in terms of 1,000 years or more. So we cannot get back the old geological kind of normal behavior for thousands of years, I think. But if we are just talking about the surface of the Earth and can we make it less hot to maybe something like the standard now is always to think about pre-industrial. We cannot bring it back to pre-industrial either because in the short term, what we see is that the accumulated CO2, it causes linearly the temperature increase. So without removing the CO2 that is already in the atmosphere, that means all the industrialization that happened since the invention of the steam engine and all that CO2, as long as it stays in the atmosphere, we are committed to a certain warming compared to pre-industrial time. That cannot be undone. So what we are talking about all these few decades is how to stop it from getting worse, how not to put in more CO2, how not to cause the warming to be worse. And so Jean showed a slide where to reach that, to be within that 2-degree warming from pre-industrial average, we have to totally be carbon neutral by 2080 to 2100. So, so we are just talking about not putting in any more CO2, and that's all we heard about. The CO2 that's there is committed, the change there, but the consequences have not worked themselves out. So even after we stabilize the CO2 content, we stop emitting CO2 in the net by the end of the century, if we do that. So the first response is that the warming will be, the transient response will be 2 degrees. But system needs to adjust after that. The climate system is a non-linear system. So far the linearity comes in because so far we are taking it, the first response is quite linear. But when the feedback kicks in, there will be consequences. When the biological systems that our third speaker talked about adapts, or when species don't adapt and die off, those consequences will come. So even beyond 100 years, the consequences will still work themselves out. So even in terms of pre-industrial normal is not possible. Keeping things the way they are, well, in terms of warming, if we manage to reach our target of 2 degrees Celsius, we still have to suffer the consequences working themselves out. So that's not quite normal. In other words, you won't get normal, really, not in that sense, but you can get a new normal. You can adapt yourself, and then you'll be happy with that, maybe.
Well, I think the only bit you've missed is this sort of sea level, because, well, and the oceanic response as well, because the oceans respond on much slower timescales than the atmosphere. So we could sort of fix the warming in the atmosphere side, but we would still then have this commitment to thermal expansion and sea level rise and warming of the ocean. It would take the oceans very much longer than decadal timescales in order to come back to any kind of equilibrium similar to what we had at the pre-industrial times. So I think we have this way, and I think maybe it is the fault of or an issue because of the Intergovernmental Panel on Climate Change. We tend to look out to 2100 and not to then think about what's going to happen beyond that, but actually, as you have just said, we do need to look beyond 2100, and particularly with respect to the oceanic response, we need to look into the 22nd century.
I don't have a whole lot to say except not within our lifetimes. We're not going to make, it's not, we need to do all we can to mitigate, but we're going to see warming throughout our lives. Maybe our children or grandchildren, people of your age, maybe your children or grandchildren, might see something positive if we can actually do something about it now.
May I share? Maybe audience know about the technology of reverse osmosis. This is to convert the seawater become, we call it pure water. This is just dream 40 years ago when I was student like all of you. When I'm student, this is impossible to convert the salt water become a drinkable water. This is what I'm still thinking about optimistically, that if my unit can run for an industrial basis, it could be run also in the housing. Why? We use solar to produce the electricity, injected to the unit, then any CO2 out from the house is compared become the gas, then like cycle. But this is just dream, might be 40, 50 years ago. Next it will become, I don't know. But this is part of my dream. But need a technology and need a policy for it. Thank you.
Okay, thank you for all the speakers. Let's move to the QA segment. I will inform you how this segment will go to work. First, this QA session will going into 20 minutes. If you have a question, please go to nearest mic there on the right side, a center, and the right side. And the second is, okay, that's all. Now we begin the first QA segment. Please go forward. Thank you.
Good afternoon. My name is Fauzi Fartakin. I'm from Universitas Islam Indonesia, Yogyakarta. And my question to Mr. Ko and Ms. Jian. What is your opinion about the people who say climate change is just hoax? And there is give some proof, some fact that climate change is just gossips, hoax, and not truly happen. What is your opinion about that? And I want to ask one thing more to Mr. Ko. What you're talking at your presentation just about CO2. What about nitrogen dioxide and CFC and other greenhouse gas which have more effect than just carbon dioxide? And to Mr. Nikhil, I heard your presentation you talking about adaptation. I want to ask about the way adaptation which make a giant wall on sea, which purpose that is protect the city from flood or sea level rising, just like in Saint Petersburg in Russia and London and Jakarta, of course. Thank you.
So, a lot of the issue here seems to me, to lie with the media. So, the media seems to have this idea that it has to be even-handed and give equal amounts of time to scientists who are talking about the reality of climate change and a very small community of deniers. If the media actually balanced its coverage of the issue in order to reflect the proportion of scientists who are convinced of the reality of climate change and the very few who are not, then actually you'd almost never hear from the community of deniers. So something like 99% of active scientists are convinced of the reality of climate change. There is a very small group of deniers, but increasingly over time you hear their voice less and less, and I think that's a very good thing, because the problem with the deniers is that they delay action to address the challenge of climate change.
Yeah. I'd like to echo Jean's point. Yes, indeed. It's the impression some people get that the two sides are balanced, but actually it's not. Actually, a kind of more cynical or joking attitude is like, if they think it's a hoax, we think that they themselves are just a hoax as well. So just dismiss it. But then your question on besides CO2, there are other greenhouse gases, right? Indeed, I only talk about CO2 because in 10 minutes, I don't think I can talk about too many things. And CO2 is the largest component that is responsible for all these changes. But you are right, there's methane, there's nitrous oxide, and then there is also CFCs. So still CO2 is the most important contributor. That is true. But in terms of its impact per molecule, it is the weakest. I think just now we saw a graphic by Neil showing that CFC is the strongest, but CFC is the least abundant, right?
Great. So I think my question was on seawalls. Yeah. So in some cities, it's something that I think is the only option. You know, you might be the only option available to you. The other thing we need to also do is build further away from the coastline. You know, at the same time, we're putting up, you know, multi-story condos right on the coast. So need to be smarter about decisions like that. But given I work for World Wildlife Fund Conservation Organization, we would always advocate green infrastructure instead of gray infrastructure. It's also what we call ecosystem-based adaptation, so using nature to help you adapt. And an example in the case of dealing with sea level rise would be mangrove restoration. So rather than building an artificial structure, you actually restore mangroves, and that provides coastal protection.
Okay, thank you. And for the second question, please on my left side.
Okay,
thank you.
Good afternoon. I'm Ahmed Tawish. I'm a graduate in chemical engineering from India and doing my research in UAE. My question is basically addressed to all of you about the policies on climate change. How seriously the government and the countries have taken the Kyoto Protocol, and how beneficial can the future agreements can be viable for the climate change? One more thing, because there has been a great criticism even on world superpower like United States, Russia, China. They have not been able to control their emissions but talk about climate change, because it's now time to act. So that's my question. Thank you. Address to all of you.
Well, so our government's doing enough? No, they're not. I don't think there's the slightest doubt about this. And although the Kyoto Protocol did have some teeth, as you might describe it, and did make some progress, the real problem is that since the Kyoto Protocol has lapsed, the governments internationally have failed to put in place replacement for the Kyoto Protocol. And that's why the meeting in Paris that will take place at the end of the year is so important, because it's just about the last chance that international governments have to put in place a successor to the Kyoto Protocol that will bring all the governments to the table with binding agreements to do something about greenhouse gas emissions. So we all have to hope that they'll succeed. The probabilities, I wouldn't like to guess. I'm probably not very positive, but I'm sure that I have colleagues who are much more positive about what will happen in Paris than I am. I think I'm more encouraged by what's happening at the bilateral and even unilateral level, where governments are putting on the table the commitments they're prepared to aspire to, but those commitments are not binding on their targets. So whether or not that can deliver what we need, I think it has to be tested, because increasingly governments are not prepared to put in place binding agreements that can be policed by external organisations. They want to hold the whole thing within their own borders. So we have to go along with that desire, and we have to negotiate new arrangements that will deliver what it is that we need. So I encourage you to go to the session on Saturday at this conference, which is about the Paris meeting, and I think it will be a very interesting one. And we all have to watch and see what happens in Paris at the end of the year.
Well, I don't have anything to add, really.
Okay.
Yeah.
Thank you for the answer. Thank you.
And the third question, okay.
Hello, good afternoon. I I have a question for Professor Jean. About the climate change, we're always hearing these negative impacts. So I want to ask, are there any positive impacts? And if they are there, how do they compare with the negative impacts? Thank you.
Oh, are there any positive impacts from climate change? Yes, there are. There's no doubt about it. I don't know where you come from.
I come from Zimbabwe and I'm doing electrical engineering.
Okay. So, well, that's good to know. The news perhaps is not so good for Zimbabwe. I think, generally speaking, it looks like the impacts are going to be more negative for countries which are closer to the equator. Countries that are further away from the equator, particularly in sort of northern temperate latitude, so sort of Scandinavia, the UK, there will be, at least in the early years of global warming, we can expect that there will be, for example, increases in crop yields because the conditions are warmer, and also the effects on human mortality will be positive because many people die in countries like the UK in winter because of the rather severe conditions. So winters will become warmer, fewer people will die because of cold conditions, and it won't be so hot that people will be dying of heat stress. I have to say that in countries like Zimbabwe, it's likely that, for example, that seasonal shift in mortality will not be a positive one. More people will die because of very hot conditions, and you don't have so much that cold weather effect to be addressed. So there will be some positive results from global warming. You also see that, of course, with sea ice melting in the Arctic Ocean. Some of the very northern governments are very positive about opening up new transport routes through the polar seas. So depending on your position, you might see that as a positive impact.
Thank you.
Is there any speaker that will answer? Okay, no. Okay. The fourth question.
Hello.
Please.
Hi, I'm Dan from New York. I had a question. It's more on sort of the disparity that I see between developed nations and developing nations in climate change mitigation and adaptation. There has been in the past couple of years some starts to help lesser developed countries, particularly in sub-Saharan Africa, deal with climate change effects. You know, there have been African risk capacity programs that help with climate change mitigation and adaptation. There have been some new initiatives, especially because of the post-2015 development agenda and sort of the need to push for more sustainability. But I think we are definitely still behind in making sure that developing nations can address these issues equally. So what do you think is important to address, and how do you think we should address the issue? Do you think a governmental push, more of an economic push that's led by corporates? How do you think we should address the issue of lesser developed countries having slower growth in terms of climate change adaptation and mitigation? Thank you.
Okay, what speaker that will be addressed?
Anybody, honestly. I
Okay.
think you can all answer the question.
Okay, thank you.
I'll take a first stab at it. So I actually do quite a bit of work in sub-Saharan Africa, where we're working in Kenya and Uganda quite a bit, looking at the kinds of change people are experiencing and how they're responding to it. There is a role for the private sector, as you mentioned. I'm not too much in tune with that. In a lot of these countries, it really is being led by the government. Both Kenya and Uganda, for example, they don't have dedicated ministries, but within ministries, they have dedicated units devoted to climate change. So it's something that they really realize that they have to deal with. And I think they are starting to do that. You know, they're providing things like short season variety crops for rural communities. In a place like Uganda, something like 8% of the population farm. So they really are being impacted by this. On a global scale, just within the next few months, actually, the Global Climate Fund, GCF, is going to go live. And that's sort of a similar structure to GEF. And this is going to provide, their intention is that it be split 50% between mitigation and adaptation. And then there's a bunch of implementing agencies, and WWF is actually likely going to become one in October. And what this is doing is it's taking all this funding from developed countries and making it available to developing countries. So we're hoping that will be a useful financing mechanism The numbers being thrown out there are ranging from 10 billion to even as high as 100 billion. So there's a lot of money that's being brought together for this. The key thing now is that we need to use it wisely.
Is that necessarily a new model, though, the funds model that started?
Well, the GCF is a new agency that's coming up now. That wasn't there previously. Previously, we had things like the Adaptation Fund, which was very small. The GEF itself had a climate change division, again, fairly small. So the GCF is going to be the largest thing of its kind. But the key thing is that this money is used well. A lot of what people call adaptation is actually just business as usual. So people really need to be using the funds well and actually using climate data in an effective manner as well.
Thank you.
If I may, I just would add that I do have colleagues who work in adaptation in developing countries who would say actually that community-based adaptation in countries like Bangladesh is way ahead of anything that we're managing to do in developed countries. So I think there are arguments that around actually developing countries doing a little bit more in adaptation, mainly because the risks are more imminent, and also I think because in a way they've almost got less to lose. So adaptation in developed countries implies change from what for many people is a very comfortable norm, and that change is actually quite threatening. In developing countries, adaptation can mean improvement. And so I think you'd have to explore your question a little bit more to be sure that it actually stands up that developing countries are doing less than developed countries.
Thank you.
Okay, for the last question, I'm so sorry. For the last question on my side. Okay.
Hi, good afternoon. I'm Irish from the Philippines. I'm a student of BS Human Ecology majoring in human settlements planning. Now we are all aware that due to rapid urbanization, climate change and its effects are getting worse. Now my question is, how important is urban planning, specifically human settlement planning, in the reduction of CO2 and greenhouse gases in the atmosphere and in mitigating the effects of climate change?
Do you mean to ask, like, by changing urbanization pattern, can you reduce the carbon footprint
Yes.
and the emissions? I think so. Like, if you in your urban planning, you make sure that you are more energy efficient, right? If you have buildings that are green, that have zero carbon footprint, skyscrapers take a lot of energy, shopping malls take a lot of energy, public transport systems. So all these, if you do your planning well, and it can make a huge impact because many people live in cities. What's the second part of your question?
How is human settlements planning important in mitigating the effects of climate change?
So I mean, when you reduce carbon footprint, right, then that would mitigate the climate change impacts. Yeah.
Well, over half of us now live in cities, so if we don't fix it in the cities, we're not going to fix it at all. That's the bottom line, I think, in terms of... so it's not just a question of mitigation, actually. Urban areas are a very, very good example of where we have to bring adaptation and mitigation together, and we have to develop strategies that deliver to both. So there's a risk if you adapt in an urban environment by increasing the amount of air conditioning and you generate the electricity using fossil fuels, then there are no co-benefits there. You're actually making the problem worse. So it's very important in urban areas that we have integrated solutions that deliver to both adaptation and mitigation. And an example might be, for example, greening of cities, which can reduce their carbon or their greenhouse gas emissions and can also make them more comfortable environments to live in.
Thank you.
Okay, due to limited time that we have, I'm really sorry that Q&A segment will be over. Before the session ended, I please Akhila to move forward to give the speaker a memento. Okay. Okay, we can stand up to. Please give us. This. Thank you. Third is Mr. Kodeyang. And last is Mr. Nikhil Advani. Okay. Okay, thank you for the speaker. Thank you for all delegates. Good afternoon. Okay, thank you. To all delegates, actually we have information. Coffee break will commence after the session and refreshment will be served in the pre-function hall. Following the break, we will be returned to Pecatu Hall for the Emerging Asia at 3:30. So be sure to head in early to get a good seat. Also, I would encourage all of you to check out the research corner at the top of escalator at the same point. Thank you.